These are the notes on electronegativity. Now, electronegativity is a big, long word, one of the million-dollar words in chemistry. This is something you really need to understand if you're going to understand chemical bonds. We've already talked about the octet rule, how most elements would like to have 8 valence electrons. Well, that makes it sound like they have a choice. That makes it sound like there's other options. But actually, they need to have 8 valence electrons. Only the noble gases are the lucky ones that have it to begin with. So other elements need to make chemical bonds of various kinds in order to achieve an octet of one kind or another. One method of achieving an octet of sorts is making an ionic bond. So this makes salts. Salts are ionic compounds and they have high melting points. We talked about the way they form, sort of. We talked about the way they stick together more and the properties of those. So that is one option. You can make an ionic bond. And if that makes you have an octet, either by going up to an octet or dropping down to your inner octet, then that's fine. But we need other ways to do it also. Remember that some elements are so far away from having an octet, if you only have one valence electron, Lewis dots, remember, are the valence electrons. All the ones on the left side of this diagram have too few valence electrons to really ever go up to an octet, ever gain enough electrons to get an octet. We just really don't see that happening. So for the ones, I hate to break it to you guys, but you elements that are on the left side there, you're not going to make it. You're better off losing your electron. And then remember that underneath that one little valence electron or two little valence electrons or maybe 3 valence electrons, underneath, if you get rid of those, there's got to be an octet underneath. There's got to be, because a noble gas fills before you go to the next energy level, right? So remember, that's one way of getting an octet. Or if you're close enough, like let's say the family with nitrogen on the top, with N on the top, or O on the top, or F on the top, okay? That's the nitrogen family, the oxygen family, and the halogens is the fluorine family. Those can make it. All they need is 1, 2, or 3 more electrons, and that's doable. So we see those form ions by gaining electrons, picking up a negative charge, and the other ones lose electrons, which winds up giving them a positive charge. These, of course, would be the anions and the cations that we discussed last time. What I had to leave out of the last notes, because we were running a little too long on time there, is that you can predict the charge on the ions that will form based on their position relative to the noble gas. In other words, look at group 17 there that has F at the top, F minus, I guess that's a really bad grade. Well, that's the halogens, and the halogens are so close to having a noble gas octet of electrons in their valence shell, each of them only needs to gain 1 electron. Well, if you gain 1 electron, you get a -1 charge. Chemists do not like to write the number 1 when they can avoid it, and so instead they just put a negative sign. That means -1. Things in group 16, which is the oxygen family, okay, in the oxygen family, they need to gain 2 electrons, so they have to pick up 2 negatives. That makes it -2. Chemists like to write it backwards, 2 minus. It's just the way they do it, and they write it as a superscript that is not an exponent. That doesn't mean oxygen times oxygen and negative. No, that's just the charge. So they write the charge up, and the reason they do that is because they write the subscript below, which tells you the number. So that is always a charge if you see it up and to the right. And then, of course, the nitrogen family, the next one over, has to gain 3, so it gets a -3 charge, and so on. If you go way over to group 1, well, obviously they lose an electron to get down to their inner octet. So if you minus -1, that gives you +1. And so their charge is +1. Again, chemists don't write the ones, and it's just a little plus sign up and to the right of the symbol of the element. By the way, please note that the second letter in any symbol for an element is always lowercase. We never see 2 in a row for one element that are capitalized, and I've been seeing that mistake quite a bit on assignments. Okay. Group 2, the next one over, well, they need to lose 2 electrons. Minus -2 gives you +2, which is their charge. And of course, they write it backwards. They write 2 plus. So you can actually predict a lot of the charges of ions on the periodic table, well, at least in these groups. It's very, very easy. And that is why, do you notice the ones on the left form positive ions? What do we call those positive ions again? Meow, cations. And then the ones on the right side, other than the noble gases, well, they form negative ions. What do we call negative ions again? Anions. So cations form on the left, interesting. And that's where metals are. Anions form on the right, interesting. That's where the nonmetals are. This is going to come into play very majorly. So what if you're not lucky enough to be in the S block on the left or the P block on the right? Those are the ones I showed you on the previous slide, where it's really easy to predict what the charges of the ions will be. Well, if you're in the D block, for example, it's not so easy to predict what the charge of the ions will be. So it has to be told to you. So how do they do this? Well, they use Roman numerals. Roman numeral 1 is I. Roman numeral 2 is II. Roman numeral 3 is III. So, and then 4 is IV, etc. So why do we do this? Because look, what do all of these charges have in common? They all have a plus. No matter what, anything in the D block, any metal, will make a positive ion when it makes an ion. So the tricky thing is some of them, notice, can make more than one. In the case of indium, you got 3 different ones there. So you got to know which one you've got. So it has to be told to you. This is way beyond the scope of high school chemistry for you to predict what charge the ion would have in the D block. You can think about them all as having 2 valence electrons, sort of, because of the shave before dressing thing in the electron orbitals. The following S is filled before you get to the D block. But anyway, so let's look at an example. Look at where it says group 8. Just below that, do you know what element that is? Fe. That stands for ferrum, and that is the word for iron. So that is iron. Notice iron can have a 2 plus and a 3 plus charge. So how do we indicate that? We write it out. This is how we indicate the ion with a positive 2 charge. Iron 2, that's Roman numeral 2 in parentheses. How do we indicate this one? We write iron 3, okay, Roman numeral 3. Sometimes it's given in parentheses and sometimes just written next to it. So those give away the charge of the ions. That tells you the charge of the ions right there. Otherwise, it'd be very hard for you to know. So just be on the lookout if you're wondering, what do they mean by those numbers, by those Roman numerals? This is what they mean. And the great thing is they're always positive because metals form cations. This brings us to another way that you can satisfy your octet. Well, actually, this is one that can be easily understood looking at a very simple example. Like many things, it's usually easier to understand the simplest example of something. And in this case, it involves hydrogen. In fact, chemistry often understands things using the element hydrogen because it's just so simple. All hydrogen really is a proton in the nucleus with 1 electron attracted to it going around it. So if we look inside of a hydrogen atom, like the one on the left, inside, well, there's a proton there in the middle, that little plus. And of course, that proton is the reason that electron is there. That electron, that negative, going around in that blue area, is attracted by the nucleus and orbits in the first energy level in the 1s orbital. It's 1s1. But keep in mind, that electron is also attracted to anything else that's positive, anything else nearby with a positive charge. And that proton is also attracted to anything else nearby, anything else with a negative charge. Remember, opposites attract. So what about this nearby other hydrogen atom? If we look inside that one, we can see that, oh, there's another proton, of course. And that proton is attracting the electron of the first one on the left. It's also attracting its own electron that's below. And the proton from our original hydrogen atom on the left is attracting that electron from the other hydrogen atom. Meanwhile, the two protons are actually repelling each other because they're both positive, and the two electrons are both repelling each other because they're both negative. So the question is, what's going to win, the attraction or the repulsion? Well, it depends on the distance they are apart. If the hydrogen atoms are far enough apart, then the attraction between the proton in each one and the other one's electron is greater, and it pulls them closer together. And this continues to happen until the repulsion of the two nuclei, the two protons, wins out and it pushes them back. And what you wind up getting is a stable distance that those two protons would like to be apart, okay, where they don't really want to get any closer together because of the repulsion, but they don't really want to get any further apart because of the attraction. And this is called a covalent bond. In a covalent bond, what you wind up doing is sharing electrons. Covalent bonds share electrons. So imagine if you have your two arms, right? And each arm goes to grab the opposite elbow, okay, sort of clasping together, almost like an ancient Roman handshake. Okay, that's kind of what a chemical bond is. It's the nucleus of each atom trying to grab not only its own electron, but also that other electron in the neighboring atom. Now keep in mind that hydrogen atoms are identical, so they're both kind of doing the same thing in a mirror image. They're each trying to go after the other one's electron. And in trying to do that, they wind up stuck together in a covalent bond like we see on the right side of the diagram where a covalent bond is formed. So here we have a hydrogen molecule. In a hydrogen molecule, they are sharing the electrons. In fact, both of the electrons are shared between the two nuclei. It's kind of hard to say which electron fully belongs to which atom, and they wind up locked together. Now they think they're noble gases. Now why would you think you're a noble gas? That is certainly not an octet, right? Not even close. But remember, hydrogen is in the first energy level. In the first energy level, there's only one noble gas, and it doesn't really have an octet. It's the exception, right? It is helium. So let's look at the hydrogen atom. This is how we show the Lewis dots for hydrogen. Notice that on one of them, I have the dot on the right. On the other one, I have the dot on the left. That doesn't matter. It doesn't matter which side it's on, as long as it's on one of the four sides. Okay, so if these two hydrogen come together, well, they have a way of showing this. We have a special way of showing the bond that forms. Watch. That is a covalent bond. So that dash, it's a long dash, it indicates that you are sharing a pair of electrons. It turns out individual electrons can never be shared. Only pairs of electrons. And one electron needs to come from each side, from each of the two atoms. So that doesn't seem like a lot of electrons too, but the funny thing is that each hydrogen seems to think it is in possession of both of those electrons. Each hydrogen is now dreaming that it is helium. Now they are not helium. They have not changed their protons. They still have just one proton in each nucleus. Helium, of course, has two. So it's not helium, but it seems like it is. It's got two electrons going around, and that is a noble gas configuration. Now this is not an octet, but it is a simple example of an element thinking that it has a noble gas electron configuration. In this case, it's more of a duet, it's only two, by sharing electrons. And again, this is the hydrogen molecule, the simplest of all the molecules there is. Easy to understand. They're sharing those two electrons. Each of them thinks they have both. That's kind of delusional, but atoms kind of are delusional sometimes. And they think they're like noble gases. They are way more stable like this than they were separated. Now, I'm not saying that hydrogen gas is stable, because hydrogen gas will still go on to have many, many other reactions. But this is incredibly more stable. So much more stable than an individual hydrogen atom, which you just don't find. That is so unstable to find an individual hydrogen atom that you never actually come across those. So we saw ionic bonds. That was the first one we saw in our last notes, where cations and anions are attracted to each other, forming a crystal that is hard and brittle. Well, this is different. This does not form a giant crystal lattice, because now we're talking about covalent bonds. That's something different. Covalent bonds share one or more pairs of electrons, and that's it. That's the end of the bond. It doesn't go on and on and on like in an ionic bond where you keep getting alternating cations, anions, cations, anions. It's not like that. It has a very discrete direction and length, and that's the end, and boom, your bond is over. So because of that, covalent bonds form these little itty-bitty little creatures that we like to call molecules. Molecules have a very specific size, and they have a very specific end. They only go so far. So you can see the hydrogen molecules there we've already discussed, and here's several other molecules that we'll be seeing a lot of, and that's really all there is to them. They are just very discrete, small little particles made up of just a couple, or well, sometimes they can be long, but sometimes they're only 2 or 3 or 4 or 5 or 6 atoms stuck together. And by the way, they're still atoms because they didn't really become ions. They didn't really gain an electron, did they? Those hydrogen atoms we saw, they didn't actually pick up an electron. They just sort of think they have the other one's electron. So in molecules, these guys are still atoms. They are not ions. Let's talk about energy. This is one of those concepts that students generally struggle with. This is not a very easy concept to think about, but I am going to try to put it in terms that maybe you can understand. So this is what we call potential energy. It's given in kilojoules per mole. We don't need to worry about that. Let's just call it energy. Okay. Now, a lot of people think energy is great. I want to have a lot of energy. I want to go climb a mountain. It takes a lot of energy. I want to go on a bike ride. Okay. I need a lot of energy. Or students run LA. I want a lot of energy. But the world of the atom is very, very different. Atoms don't want to have energy. They want to get rid of energy. They want to have the lowest possible energy. They always do. And it turns out, why is that? Because the lowest possible energy, where is that located? It is on the floor. So if you're on the floor, you actually have very little energy. Like obviously, if you're lying down, that is the lowest potential energy. When you drop something and it gets to the floor, it doesn't have any further to fall. Think about it that way. So in the realm of atoms, you can have hydrogen atoms. I'm going to put those in off on the right. See where it says A? Boop. There's your hydrogen atoms. And if they are separated from each other, well, that means they have a lot of potential energy. They could fall together. Like think of each one of them is the other one's floor, so to speak, if that works. So they can fall together. And as they fall together, their potential energy decreases until they collide. Watch. And then they are together, stuck together in a hydrogen molecule. Well, it turns out that is very stable like that. At least it's a lot more stable. It's a lot lower energy than where they started. It's down in the pit. The bottom of a pit is a stable position. Okay. But in order to get there, because they had more energy to begin with, energy had to be released. Energy is released when atoms form a covalent bond. So where is that energy? Well, it's given off as heat and light. It's gone now. And then the atom is stuck together. What if those hydrogen atoms try to get closer together? What if they try to squeeze even closer? Well, watch what happens. The potential energy goes back up and it pushes them back the other way. Kind of like if you try to roll a bowling ball up a hill, it's going to roll back down to you. It's kind of hard to get a bowling ball to roll up a hill. You need a lot of effort to do that, a lot of energy. And the same thing goes with that hydrogen molecule. If you want that hydrogen molecule to break apart again, well, guess what? You have to put that energy back in. So if you blast them with the same amount of energy that they have already released when they formed a hydrogen molecule, it will once again knock them back out of that energy pit and separate them again, and they'll go on their merry way. So here is a cartoony version of that happening. Now, the thing that often confuses students about this is that the energy is negative there. Notice on the left, and the energy at the top is 0. It's really hard to think about negative numbers in many, many ways for the human mind. So let's not think about it as the energy that was already released, as a negative energy that has already been given off. Let's think about it as what we call the dissociation energy, the energy it would take to put back in to smash them apart. So watch what happens. I'm about to blast those apart, knock them back out of the well, and the amount of energy that just took was exactly the same amount of energy that they gave off when they formed. So rather than thinking of it as a negative energy that's already missing, that's a little tricky. Think about it as how much energy would it take to blast those hydrogen atoms apart again? It's the same amount, but that direction would be positive. So I think it's easier to consider how much would it take to break them apart. One thing that I want to mention is notice where it says 75 ppm, that's picometers. That is the separation of the two nuclei. That is called the bond length. Now, bond lengths will tell you something about the strength of the bond. It turns out, if you have a shorter bond length, that means you have a stronger bond. Shorter bond lengths are harder to break apart. They take more energy to separate. If the bond length is really long, then imagine the two atoms are just barely clinging to each other, really, really easy to knock them away. That's not a strong bond, okay? So bond length is related to the bond energy, or dissociation energy if you want to think of it that way. And the shorter bonds are stronger, the longer bonds are weaker. So we've talked about the octet rule, and now you probably want to see a for real octet forming. Not a hydrogen duet, that's kind of bootleg. So let's see a real one. Fluorine, the most often misspelled element. Fluorine, F-L-U-O. It's not pronounced like that, by the way. It's fluorine. Fluorine has 7 out of 8. It's so close, and it knows it. It desperately, desperately wants to get that remaining valence electron. So the fluorine on the left is thinking that, and so is the fluorine on the right. They're both extremely desperate to get the one electron they do not have. So the fluorine on the left goes to grab an electron from its neighbor. The only electron, it turns out, that it can even try to get a hold of is that one unpaired electron. See that odd electron there? That's kind of how you know it doesn't have an octet, because an octet will never have an unpaired electron like that. Those other ones appear to be paired up, at least the way we do Lewis dots, which is based on sp hybridization. You'll see in your textbook. So if the fluorine on the left goes to grab that one lone electron from the fluorine on the right, and the fluorine on the right goes to grab that one lone electron on the fluorine on the left, this is what happens. Exactly like hydrogen, they wind up sharing both of those unpaired electrons in a covalent bond. So that covalent bond counts as 2 electrons. It counts as 2 electrons for the fluorine on the left. But it also counts as 2 electrons for the fluorine on the right. Hey, wait a second, that doesn't make sense. That's double dipping. That's counting the same thing twice. But this is what atoms do. They seem to think they're delusional, and they seem to think that they each have possession of those 2 electrons, that pair of electrons. And so what we say here is that fluorine now has a satisfied octet. We count the covalent bond as 2 for each side. So notice that the fluorine on the left has 2, 4, 6, and then the bond counts as 2 more, that's 8. And the same thing goes for the one on the right. So here they are dreaming that they're neon. We know they're not really neon. They want to be like neon. Everybody wants to be like neon. Neon's perfect 10. But they can't really do it. They can't change their protons. So the closest they can get is faking it. Making an octet. We really count this as an octet, by the way, in chemistry. This counts. But what's the side effect of this? What's the catch? Well, it's stuck to another fluorine atom pretty much permanently until there's a chemical reaction. So you can't just be neon, which gets to float around in individual atoms, bouncing around happily. You got to be stuck to something. To maintain your octet, those two fluorine cannot separate from each other. And so now we have a fluorine molecule. Now, I'm not saying a fluorine molecule is stable. You do not want to have fluorine molecules in the room with you because it's a poisonous gas, a very, very dangerous chemical. But what I'm saying is those fluorine atoms are so much more stable, so much more stable in that molecule than they were separated. When they were separated, that is ridiculous. That is something so unstable that we never actually find it in nature. We just don't find it because it just can't last for even a moment. So fluorine kind of has to do this. Pretty much every atom has to make some kind of an octet one way or the other, with very, very few exceptions. Very few. So this doesn't add up because if they were both neon, well, those two electrons, they can't both have those two. Each one of them really has one of them. But this is the way they behave, so you know what? We give it to them. We say, okay, sure, fluorine, you've got both of those electrons, and we say the same thing to the other one. So it is delusional, okay? But it is possible to make two octets out of only 14 valence electrons. Of course, two octets should need 16. So it's a little delusional. Now, there are three basic kinds of bonds. You'll hear a lot of things referred to as bonds. Some things are not proper bonds, like hydrogen bonds are not proper bonds. These are the three proper, for real, chemical bonds: metallic bonds, ionic bonds, and covalent bonds. Well, metallic bonds we're going to get to later because they're easy to understand if we know the other two first. So we'll get back to those. Let me just say this. Metallic bonds always form between two metals. If you have only metals, then you definitely have metallic bonds. I'll say that. We'll get back to the rest of it later. Ionic bonds we learned about in the last notes. That's where you form a cation and an anion, see the plus and the minus, and they stick together, and it forms a salt crystal and all those properties. We already saw that. Okay, so potassium chloride is the example given here. And then there's covalent bonds. Well, we just started talking about covalent bonds, and that's where you share electrons. Neither one of them is an ion. You have no cation, no anion. They're still atoms, but they're stuck together, imagining that they have control of those shared electrons, thinking they have an octet. So these are all different ways of basically getting your octet one way or the other. And the example here is chlorine, another deadly gas. Chlorine gas, you don't want to have that around. Very, very deadly gas. If you see a green gas, you probably want to go the other direction, probably rapidly. So I've made my own little poster about metallic bonds, ionic bonds, covalent bonds, and this is a very, very simplistic, summarized view of what the differences are. So I'll read this even though we aren't getting into metallic bonds yet. In metallic bonds, electrons are loosely shared, forming an electron sea around the metal, quote, cations. I'll get back to that later. I don't really want to go into that. Ionic bonds, the middle one, electrons are transferred, making cations and anions, which stick together in a salt crystal. Okay, well, the only part of that that isn't entirely true is the electrons aren't always transferred directly between the cation and the anion. Often there's a process by which that occurs, but in the end, it's the same result. You've got cations and you've got anions, and they stick together just like that image there. That is actually the most accurate of all of these images, the one in the middle. That is really what we see when we zoom in on a salt crystal, ionic bonds. And then, of course, there's layer upon layer. That's just a slice through a salt crystal. And then now we've got covalent bonds, the green ones on the right, where electrons are tightly shared between two atoms, making molecules. This is how molecules form. You've all heard of molecules. They're famous. Molecules is one of those great words in chemistry that we love to use all the time. But only covalent bonds form molecules. Ionic bonds do not. Metallic bonds do not. So we can't just go around calling everything a molecule. There is a very specific definition to what constitutes a molecule. And that is what we call the molecule club. I like to call it the molecule club anyway. It's a very exclusive club. If you want to get in the molecule club, you have to submit your application, and then they review it very, very carefully. They're very nitpicky. And one of the things you must have is you must only have covalent bonds. It must also be composed only of atoms. Now, you may or may not be polar. That's something they accept. Either way, polar or nonpolar, that doesn't matter to the molecule club. Molecules usually are made mostly of nonmetals, although that is not a steadfast rule. That is a rule that varies a bit. And they are free. They have no net charge. That's important. Molecules must have no net charge. Generally, they have low melting and boiling points. That's a property they have. No ions allowed. That is a stickler. If you are an ion, or if you even have an ion as part of you, you're trying to get in the molecule club, excluded. And so, unfortunately, polyatomic ions, which are very, very commonly forming ions and look an awful lot like molecules, man, they look like molecules, almost identical in many ways, they are excluded from the molecule club. So the molecule club is an exclusive thing to get into, and you need to fulfill a lot of these requirements. And there's a few things they're flexible on, like polarity, okay? So we'll get back to this more later. So I like to say, this is how you remember what molecules are. Anything that doesn't meet these requirements is not going to be a molecule. Electronegativity. Boom. The big word, the title of these notes. This is what we need to know about the most in these notes. Electronegativity is how strongly an atom pulls on another electron. So this doesn't exactly, although it does relate to the electrons the atom already has, like its regular inner electrons and its regular valence electrons, like the Lewis dots. This is talking about how much an atom will reach out, try to grab another electron coming from elsewhere, from another atom or just floating by. So it turns out electronegativity varies across the periodic table. It is a trend on the periodic table. It's a very good trend. And nonmetals have the higher values, metals have the lower values. That means you have higher numbers on the right, lower numbers on the left. Here is a very detailed electronegativity table that I made using numbers given to the hundredths place. Now, a lot of people don't bother doing electronegativities this exactly. Usually they'll just round it off sometimes to the tenths place, sometimes even to the nearest 0.5. I've seen that. But for the purposes of what we're doing, we want to try to be precise. And this is the same electronegativity table that I'm going to attach to assignments where we need electronegativity. So notice that below every element's symbol, you see its electronegativity. That is not its atomic number. That is not its mass number or anything else. That is the electronegativity. Also notice that some elements are not given numbers. That includes the noble gases on the right, and that includes some of the ones on the bottom that we have not been able to measure it for, because it's difficult to measure it for radioactive elements. So the ones on the bottom, it's just because we haven't been able to measure it. The ones on the right, it's basically because they don't have electronegativity. Because remember, noble gases, they don't want to grab another electron. They want to stay the way they are. So notice that the electronegativities vary, and the higher numbers are on the right. Look where the green ones are. Most of those are pretty big numbers. They're like in the 2s. That doesn't sound too big, like in the 2s or in the 3s. None of them quite get up to 4. If you notice, fluorine is the highest number there. Fluorine on the upper right, near the upper right, is 3.98. Now, many people just round that off to 4, but there's a reason I don't do that, and that's because it can make a difference sometimes. If you round it to 4, you might get the wrong answer sometimes. So I like to be a little more precise with the ones we can be. Okay, so electronegativity, what does it tell you? It really doesn't tell you very much. On its own, it doesn't tell you much. These are numbers that Linus Pauling pulled out of his hat to assign to elements, and he rated them compared to each other. So this is just a relative thing compared to each other. He liked the number 4 for some reason, and he decided to make that the upper limit. So in electronegativity, the highest you can go is 4. So look at fluorine. Fluorine is right up at the top. And then he didn't go down to 0 for whatever reason. He thought there might be things even below what we've measured now. So he made the bottom cutoff 0.7. So that seems strange, and Linus Pauling was known for being very eccentric. He did a lot of interesting things. He did a lot of research into DNA as well. But he came up with the scale, and we've just sort of gone with it. People have refined it over the years, but nobody has completely redone it. He could have made the top 100, could have made the top 10, but he decided to make the top 4. So just keep that in mind. So anything that's near 4 is a very high number. Anything that's near 0.7, or let's say lower than 1, is a very low number. Okay? So what would be a middle range number? Like 2.2, right? 2.2, 2.1. If you're above 2.1, let's say you're in the higher ranges of the values. If you're below 2.1 or lower, you're in the lower range. And if you notice, all of the non-metals, except for noble gases, and I guess tennessine, which hasn't been measured yet, all of the non-metals, with a few exceptions like noble gases, are above 2.1, so they are higher values. Most of the metals are below 2.1, but there are exceptions. If you look, there's a pocket found in the D block where there are some that have higher values. Those are exceptional metals. But for the most part, metals have low numbers, non-metals have high numbers. So what matters is not so much the electronegativity values themselves. What matters is the difference between them for any two atoms that are making a bond. If you have two atoms and they're making a bond between them, you can predict what kind of bond will form by their difference of electronegativity. It turns out if there's a very low difference, like 0 to 0.5, they form what is called a nonpolar covalent bond, seen on the left. That is where electrons are shared perfectly evenly. If the difference is a little bit greater, 0.5 all the way up to 2.1, then you form a polar covalent bond where electrons are still kind of shared, but it's not exactly evenly anymore. One of the atoms is hogging those electrons, hogging them more of the time, developing a little bit of a negative charge on one end, pooling up the electrons on one side, leaving behind a little bit of a positive charge on the other end. Those are called delta positive and delta negative. See those little symbols there? That means it's a little bit positive on one side, a little bit negative on the other. The negative side would be the side where the electrons are spending more time. Okay, and then if it's 2.1 to 3.3 difference of electronegativity, well then you just get an ionic bond. That means the electrons are no longer shared. An electron is completely stolen by one, which is the one that becomes the anion, and it is completely lost by the other. So what matters is how much do you want an electron? Do you both want it equally? Then you fight over it. Okay? Or does one of them want it way more than the other? Well, then it is completely stolen. It's like a knockout victory. Okay? So think of this as like a battle over electrons. It's either a close fight, or it's hard to tell. Okay, it's an uneven battle, lopsided battle, or it's just a clear-cut knockout, an immediate knockout fight right away. So this leads us to our rules of thumb. Differences in electronegativity values provide a model where you can predict the bond type that will form. One thing I want to mention, oh, by the way, metals on their own, if you only have two metals, you do not go by these differences. If you only have two metals forming a bond between them, whether it's two of the same metal, like 2 potassium, or let's say potassium and silver forming a bond, then you do not go by these differences because metals left on their own form metallic bonds only. So this only applies if one of the atoms is not a metal, right? If one of them is a non-metal or metalloid, that's the only time when you need to use these differences. Got it? So there are rules of thumb that we use when we're predicting bonds, and these are usually pretty good, although there are many exceptions. There's a rule of thumb that covalent bonds form between two nonmetals. Now, while that is true, if you have two nonmetals, they will form some kind of covalent bond. It turns out there are other ways to form covalent bonds. So that rule of thumb is pretty good. It goes pretty far, but just keep in mind there are some other covalent bonds that'll form in other situations in addition to that. And then the second rule of thumb is pretty good. It's that an ionic bond will form between a nonmetal and a metal. So if you have a metal and a nonmetal next to each other, forming a bond between them, they're from those different categories. Generally, they'll have very different electronegativities. The difference will be really big, and generally, they'll make an ionic bond between them because of that big difference of electronegativity. Okay? So the rules of thumb can be used if you really need to do things fast, but they're not always 100% accurate. Just keep that in mind. We'll see examples of that later, where they are not always accurate. So the rules of thumb are, if you have two metals, they form metallic bonds. That's the one on the left. That's a good one. Go by that one. Then in the middle, we've got a nonmetal and a metal form an ionic bond. Okay? And then on the right, we've got the one, two nonmetals on their own, no metals involved, will form covalent bonds. And again, that is a good rule of thumb. So no rule of thumb is truly perfect. The best one is the metallic bond one. And then the next best one is the one on the right, the one for the covalent bonds. And then the worst one is the one in the middle, because there are many, many exceptions to that rule, where a nonmetal and a metal might form, instead of an ionic, they might actually wind up forming covalent. But if you have to go by rules of thumb, if you want a predictor, this does a pretty good job. Let's say some of them work over 90% of the time, and the one in the middle works over 80% of the time. So they're still good. They're all good for predicting the bond that'll form. So if you only see metals, metallic. If you only see nonmetals, covalent. And if you see one of each, ionic. That's the rule. Those are the rules of thumb. And that is why in metallic bonds we only see metals. In covalent bonds we usually only see nonmetals. And in ionic bonds in the middle, we see a metal and a nonmetal. Sodium, Na, is a metal. Chlorine, chloride in this case, Cl is a nonmetal. So now I'm going to show you a few quick examples of how to calculate differences of electronegativity. I'm just going to pick two atoms, and I'm going to put them into those two little circles there. Those represent two atoms that are going to form a bond together, and we'll be able to predict which kind of bond forms. Let's start with sodium and chlorine. Now see them on the table. Sodium is way off on the left. Chlorine is way off on the right. Sodium's electronegativity, 0.93. Chlorine's electronegativity is 3.16. Electronegativity values, by the way, do not have units. They're rated out of 4. So it's like a unitless ratio. We don't give them units, by the way. And what's the difference between those? We always take the larger one minus the smaller one. And it turns out, let's see, what is that going to be? It's going to be 2.23. So what kind of bond will form from a difference of electronegativity of 2.23? Well, you should know sodium chloride is an ionic compound. And remember, the cutoff for ionic compounds is 2.1. So if your difference is 2.1 or more, then it's going to be an ionic bond. And of course, sodium chloride is our sort of stereotypical example of an ionic compound. It's the one that we use all the time. So you should have probably guessed this one. Okay, let's get rid of those. Now the next one I'm going to do is hydrogen and oxygen. Oh, so we see this bond in many places, including in water. But notice I'm just using one of the hydrogen because we look at the bonds between each two neighboring atoms. So what kind of bond is going to form there? Hydrogen has an electronegativity of 2.20. That's pretty low for a nonmetal. It's one of the lowest for nonmetals if you look at the nonmetals. Oxygen, 3.44. That's one of the highest. One of the highest for anything, for nonmetals or anybody. There's only one higher than oxygen. In fact, oxygen has the silver medal for electronegativity. Fluorine has the gold medal, the highest. So what's the difference between those? 3.44 minus 2.20 gives you 1.24. So what kind of bond would that be? Remember the cutoffs? Well, that's between 0.5 and 2.1. So what was that again? Polar covalent bond. A polar covalent bond forms when the electronegativity difference is between 0.5 up until it becomes 2.1, in that range. And we'll talk more about this later. So what about between carbon and nitrogen? This is not a bond you want to have around you because I don't know if you realize this, but carbon bonded to nitrogen, well, that is cyanide. Cyanide is a poison. So anyway, cyanide, carbon has 2.55. Nitrogen has an electronegativity of 3.04. So 3.04 minus 2.55 gives you 0.49. Ooh, that's so close. So what kind of bond would that make? That makes, well, it's covalent, but what kind? Is it polar or nonpolar? Turns out, nonpolar. So this is one of those examples I was talking about, where if you round the numbers a little bit too much, you might get the wrong answer, because look how close that is. So it turns out that just by a hair, the bond in cyanide between carbon and nitrogen is a nonpolar covalent bond. Okay, let's look at another one. Let's look at titanium and copper. Titanium's electronegativity, 1.54. Copper's electronegativity, 1.90. What's the difference between them? 0.36. So what kind of bond would it be? You're probably thinking, possibly thinking, nonpolar, right? Nonpolar covalent. But no, why not? Because titanium and copper are both metals. So we get a metallic bond. Does not matter what that difference turns out to be. If they're both metals, you will get a metallic bond. This was a trick question. This is a trick example, whatever. So just remember, if they're both metals, like look on this periodic table, the blue ones are metals, the ones that are shaded in blue. If it's two of them, you know it's metallic regardless of the difference of electronegativity. That's the important thing to remember, okay? So you can find the difference between them, and I might ask you to do that. But just remember, that is irrelevant. That 0.36 tells us nothing. We know it's a metallic bond because titanium is a metal and copper is also a metal. Let's see maybe one more. What about fluorine? And oh yeah, fluorine has a really high electronegativity, so it's going to beat anything, right? Any contender, fluorine's going to knock down. Uh-oh, unless it's another fluorine. So fluorine does have the highest electronegativity, 3.98, but so does that one. In fact, every fluorine atom is identical. So what's the difference of electronegativity? Pretty easy to subtract. 0.00, just for redundancy's sake, it's 0. So what kind of bond would that make? If there's a difference of 0, we saw this. Differences of 0 give you non-polar covalent bonds. So there is an answer to this one. So in fact, any non-metal that bonds to itself, you already know, it's got to be a non-polar covalent bond. Because every atom, every nitrogen has the same electronegativity as every other nitrogen. Every oxygen has the same electronegativity as any other oxygen. So if you get a compound like F2 that we saw earlier, or H2, which we saw earlier, or O2, we haven't seen that yet, you know that it's got to be a non-polar covalent bond between them. Boom. So that is how we establish the bond that exists between atoms. We find their electronegativity differences. That is what tells you. Not the electronegativity, but the electronegativity difference. And that's how you know if you wind up in the molecule club. Because if you have a smaller difference of electronegativity, well, then you'll form a covalent bond if it's less than 2.1. And if you have a covalent bond, if you have only covalent bonds, well, maybe you'll make it into the molecule club. But there are other things that might exclude you, and we'll get to those later. So that is the end of the long notes on electronegativity. Believe it or not, there are even more things I need to go into. I just was realizing it was getting too long. And we've already started getting into covalent bonds. So we're going to go on with covalent bonds in the next notes. Thank you.